In this video, I want to take a look at some examples of working with paired data. And so the example I'm working with is crash test data for new cars. And when I say new cars, these cars are really, really old. If you were going to look at the data set, I think one of the cars in here is a Ford Probe. So we're talking from the probably 1990s. But the idea is we're taking an automobile and we're running it at 35 miles per hour into a fixed barrier. And of course, you're doing this remote control. You have crash test dummies in both the passenger and the driver's side seats. And they have probes all over these crash test dummies, and they're measuring impact. And the idea is to get a sense of how strong, or maybe not so strong, these automobiles are, and what kind of injuries the crash test dummies are suffering from this particular type of test. And so the data in this particular case involves automobiles and a whole bunch of different measurements. We want to analyze the data to determine if a difference exists between the severity of the driver's chest injury to the severity of the passenger chest injury. And just for purposes of discussion, you can see in the data set here, and let me grab a pen. I guess I'm going over here. I got to be on the right screen. Let's see, let's grab a pen. You can see that over here, these two columns, we have the injury ratings. Now, for purposes of understanding, let's just say that bigger numbers represent bigger impacts. So big is bad, right? The higher the number, the more the impact, the more the injury, and we don't want that. So what we're trying to say, is there a difference between these two locations in the automobile? Now, one of the things we got to consider is when we look at this data, is the data paired or not? And obviously I have this in the section of the notes where we're talking about paired data, so it is paired, but why? Why would the driver chest injury number and the passenger chest injury number have anything to do with them? Why would they be paired? Well, they come from the same automobile. If you think about it, if you're in an accident. Okay, let's say that you're going to, we have this crystal ball and we know that you're going to be in an accident. God forbid that that happens, and I don't want to speak that into being by any way, shape, or form, but imagine if you were, but you got to choose the automobile. Now, I have two automobiles at my house. My wife drives a Mazda Miata, and I have a kind of a mid-size or maybe a smallish mid-size SUV. If I know that I'm going to get into an accident, I'm going to hit something, which car do you think I want to be in? Do you think I want to be in the light one, the real small one, or do you think I want to be in the one that's a little bit bigger, a little bit heavier? Or maybe I'm going to borrow my friend's Suburban, the real heavy, solid. Which do you think I would want to be in? Well, of course I want to be in the bigger, heavier, bulkier automobile, because I think that the bigger, bulkier, heavier automobile is going to protect me a little bit better than the smaller, lighter automobile. And so when we look at the driver and the passenger chest injury ratings, when I look at, I'm going to come over here, let's say, I'm going to come over here, I'm going to circle this value, this 46 and this 45. Why are those values? What do they have in common? Well, they come from the same automobile. They come from the same type of Honda. And I don't have the specific model of vehicle in this, what I'm showing you in the data set, but it's in the data set. There's another column that has the model of vehicle in there. The weight of the vehicle, okay? The 2,313 pounds. Notice that the vehicles that I'm just showing you here, and I don't show you too many, but notice that the lighter vehicles here also tend to have maybe some bigger numbers. Is there a relationship between the injuries and the weight of the vehicle? Yeah, probably. And so what we're trying to do is compare the mean chest injury ratings of passengers and drivers. And the way we're going to set it up is with a test hypothesis. Now, when you see me write mu sub d, remember another way of writing that is mu sub 1 minus mu sub 2. Now, I'm going to make another video and show you how that we generate the printouts that I'm going to show you here in a bit. And when we're working with these paired data, the software that we're using allows us to choose which the first group is and which the second group is. Turns out if we're checking to see if there's a difference between them, if we're looking to see if there's any difference at all, and we want to do a not equal to test, it doesn't really matter which one is located in position 1 and which one's located in position 2. If you want to show that they differ, it doesn't matter what the first and the second group is. However, in another problem, maybe someone wants to show that the driver chest injury rating is bigger than the passenger chest injury rating. Now the order matters, because maybe you want to do this, and I'll use D and P here, maybe mu D minus mu P. If I want to show that D is greater or exceeds, I'm going to do a greater than test. But what happens if I flip this around? What happens if I come up here? What happens if I do the passenger first minus the driver? If I want to show that the driver injury ratings exceed the passengers, that would be a less than test, right? The order matters here. If I want to show one is bigger than the other, I got to know which one is the first one and which one is the second one. Who's smarter, men or women? If I want to compare the average GPA of men and women, if I want to say women have a higher average GPA than men, well, that's a greater than test if the women are the first group, but it's a less than test if the women are the second group. Two-tailed tests aren't much thought. It doesn't matter which is the first group, which is the second group. One-tailed test, it matters a whole lot. So you got to be careful. I've been training you this semester. Words like exceeds, is less than, is below. Those have meaning, right? That tells you which direction you're looking, say in a normal curve or a t-distribution. In a test hypothesis, that helps us determine which of the alternatives we wish to test. Now I'm just going to say be careful, because when I say exceeds, when we're comparing means, and I'll have the same conversation with you when we compare proportion. When I say exceeds, when we're comparing parameters, that may not be a greater than test. That may be a less than test. You got to be careful. The order really matters here. Anyway, I'm getting ahead of myself talking about another topic. How do we do this test? Well, we need a printout. There are 4 pieces to a test hypothesis, right? There's a test, there's a test statistic, there's a p-value, and there's a conclusion. So in order to get the test, we need a printout. And this is what the printout looks like. Now, this is old school. Oops, I have my cursor on the wrong screen. This is old school. That's a not equal to sign. Isn't that weird? An older version of the software we use puts a not equal to sign as a less than greater than sign. So when you see that, and you may see this in some printouts for homework problems and different things, just know that that's a not equal to sign. Somewhere in these printouts, there will always be a test statistic. Let's see where my cursor is. There it is. Right there. And there's a p-value. Okay, so I'm going to write that stuff down. Now, I'm doing these test hypothesis, and the only thing I've talked about really with the test hypothesis is the p-value. Is there a rejection region out there? You bet. This is based on 98. Where's the number? Here it is. 98 automobiles. The number of cars, the number of pairs is 98. For each car, we've got a driver injury rating. We have a passenger injury rating. So you have paired data, but because we have 98, we have a large sample. And so even though you see the t here, you can think of it as working with a z distribution. The p-value that you see in the printout is 0.3164. That p-value follows this alternative. It's a not equal to test. That's a not equal to p-value. We're doing a not equal to test in the alternative. That's the p-value. Can we reject? Well, is p low? In this case, it doesn't really matter what value of alpha we choose. One wasn't specified here. I'll use alpha equal 0.1, but if I use 0.05, if I use 0.01, that p-value is high. That's a fail to reject. That's how we use p-values. It's that simple. If p is low, you can reject the null hypothesis. We can't. We cannot say that the alternative is true. There is, what's this? Whoops. Again, wrong screen. This is bad when I have dual screens. This word here, it should be insufficient. There's insufficient evidence to indicate that the mean severity of the driver's chest injury differs. We can't say they differ. That was a big typo, a real important typo. This word should be insufficient. Fail to reject is insufficient. If I could use an alpha of 0.32, if I could get alpha bigger than the p-value, we would reject and there'd be sufficient, but we can never take our alphas bigger than 0.10. Okay, sorry about that typo there, but make sure you write that correctly. At alpha equal 0.10, we fail to reject. There is insufficient evidence to indicate, and everything after the indicate that everything after this point is whatever the alternative hypothesis is saying in the words of the problem. And we're looking for a difference between the severity of the driver chest injury mean and the passenger chest injury mean. What assumptions are necessary here? Well, we've talked about the assumptions in the last video I created with the this information where I talked about how it works. We need random. We need a random sample of pairs. We need a random sample of cars. I don't want to go to a Ford dealership and say, hey, give me a car of your choice, because they're going to go get the armored car from the back and they're going to make their values look really good. injury ratings are going to be really small. Have car companies ever cheated? Yeah, check out Volkswagen and EPA measurements. They had a special setting in the automobile, in the engine, so that the EPA measurements, the emissions tests looked better. They cheated. They deliberately cheated. So rather than give them the option of giving us the car, we're going to go randomly select a car. We're going to take a look at the inventory, and we're going to randomly select an inventory from their inventory and choose one of the Fords on the lot. That's the one we're going to test. And so we need a random sample of cars. Independent doesn't make sense here because we have dependent data. Approximately normal, that's an assumption we talk a lot about, but we only need that assumption if we have small samples. If we had less than 30 cars, if this was 28 cars instead of 98 cars, then we would need the population of paired differences, and we'd be talking about the difference in the driver injury ratings and the passenger injury ratings. The population of paired differences would need to be approximately normal. Because we have a large sample, the central limit theorem says we don't need that assumption. And then equal variance is never an assumption that goes with this analysis. So the only thing we need is a random sample of cars. Those are the assumptions that we need. Let me mention one other thing here. If instead of the p-value, if I took this off the printout maybe, or I wanted you to solve it using some other technique, we'd be using a rejection region. And because we're working with a large sample, I'd be working with a z-distribution. If I say use alpha of 0.10, if that's the alpha we want to work with, well, in a two-tailed case, we take that alpha and we split it. We put 0.05 in both tails of the z-distribution. Now, hopefully you've done enough work where when you put 0.05 in the tail of a z-distribution, you don't really have to think twice. You know that this is the value of 1.645 and the other one's a negative 1.645. If you don't know that, get to work in the tables. Man, we've seen this number a lot. So we're going to reject if our test statistic is further out in the tail in this direction, bigger than 1.645, or less than negative 1.645. That's called a rejection region. When we look at our test statistic of negative 1.01, let me change my ink color here. Let's make it a nice teal color. The negative 1.01 falls right there. It's in the fail to reject region. So it doesn't matter if you're using p-values, you're using rejection regions, you're going to make the same decision. I don't have a lot of information to tell you about rejection regions now. They're exactly the same here when we're comparing means that they were when we worked with a single mean. They're exactly the same for the independent comparison than they are for the dependent comparison. When I compare proportions, we're going to be working with the same stuff. They're just rejection regions. So you have rejection regions and p-values are two techniques for making conclusions. All right, so that's the test the hypothesis. What about a confidence interval? Okay, so here's the printout again. You can see where right here, the 95% confidence interval endpoints goes from negative 1.6673 to positive 5 or 0.5448. And the way that we're going to look at this, it's got a negative lower endpoint, right? That's a negative number. That's a positive number. What do we say when we have a negative and a positive? We don't know. We don't know what the relationship. We cannot determine which population mean is larger. The negative indicates that mu1, the first mean, could be less than the second mean. That's what that negative number indicates. The positive number indicates mu1 could be greater than mu2. The fact that 0 is in the interval indicates mu1 could equal mu2. The end result is, I don't know what's going on. At the 95% confidence level, we cannot determine which mean is bigger. That's what we're looking at. We're looking at this printout right here. We're looking to see, in this case, we had a negative and a positive, and we say we cannot determine. In another printout, maybe we have a positive and a positive. If that's the case, we're going to say the first mean is bigger. In another interval, it may be this one where we say the second mean is bigger or the first mean is smaller. Doesn't really matter which way you say it. A lot of times when I'm face-to-face with students, I'll pick out a student in the first row who's obviously a lot younger than me. Is that student younger than me or am I older than them? You're saying the same thing, right? You're saying one is bigger than the other, one is smaller than the other. You're just flipping it around. Doesn't matter which way you say it. They're both correct. You just got to make sure what you say matches the interval. And in this case, because we have a positive and a negative, we don't know. We're not sure what the relationship is. Now, as I've said time and time again to you guys, you don't have to do the math. I'm going to do all the math for you. Test statistics, confidence interval endpoints, I'll be doing the math. You're going to be interpreting the results. You need to be able to identify the null and the alternative hypothesis in a test hypothesis. You need to be able to find the test statistic on the printout. You need to be able to find the p-value in the table, or hopefully it'll be on a printout for us, or come up with the rejection region. You need to be able to make a conclusion. In the last problem, let's see if I can go back. I don't know if this video lets me go back. It doesn't. In that last problem, I still have the printout here. How would we find the p-value if it wasn't on the printout? We would draw a z-distribution. To find a p-value, you put in the test statistic, negative 1.01 in this case. Where am I getting that number from? Right here. And you shade the not equal to. The not equal to says shade up here and shade above a positive 1.01. That's the p-value. Now, when you go to the z-value, or the z-table, excuse me, when you go to the z-table and look up the 1.01, it's going to give you some probabilities. You're going to get a number that's probably a little off. Instead of 0.3164, it might be something like 0.3162, 0.3159. It's going to be close to that value, but it's going to be a little off because the software we're using actually doesn't use a z-table to come up with a p-value. It uses a t-table with 97 degrees of freedom, and that's really close to the z-value. But when you look up p-values in tables, your numbers are going to be slightly different than what you see on the printout. Don't worry about it. It's not going to be a big enough difference to make a difference. But those are things you're responsible for. You need to be able to find p-values. You need to be able to interpret them. You need to be able to find rejection regions. You need to be able to make conclusions with rejection regions. And then the one that kills everybody, you need to know what assumptions are necessary. So as I'm going through, and the assumptions in this example are the same as the last one. We need a random sample of automobiles. That's it. We need a random sample of automobiles. Those are the things you need to be working on right now. If you can get those things down, the null and the alternative, finding test statistics, being able to find rejection regions in tables, be able to find p-values in tables, being able to interpret rejection regions and p-values and known assumptions, you're going to do really well in the final exam. So get to work, and I'll come back in another video and show you how to generate these printouts in statistics. So long.